Last August, it was announced on the Lunar Reconnaissance Orbiter's Twitter account that the LRO would be briefly dipping from 50km altitude to 20km altitude.
Today I will begin dipping down from my usual approximately 50km orbit to an orbit that will allow me to image the Apollo sites from about 20 kilometers away. Once I reach my new temporary orbit, I'll take images of and around the Apollo sites between August 14th and 19th. After that, I'll return to my 50km orbit until December.
Well, I never knew unmanned spacecrafts could social network. Later that day, however, it was announced that the new images may not be so great after all.
A clarification for my previous post. My project scientists would like to point out that there are several technical challenges associated with getting improved resolution images at the lower altitude orbit. Example, I will not slow down from my approximately 1.6 km per second, approximately 35,000 miles per hour, speed when I get closer to the moon's surface, which might cause some image blurring, particularly for the LRO narrow-angle camera images. However, it will certainly be fun to compare the images from the different orbits.
When I first read this, I just rolled my eyes. The previous images never lived up to all the hype, and so seeing the LRO team turn around and say that there may be some blurring only felt like they knew from the start that the images would be crap. Nonetheless, this certainly got the regulars from the pro-NASA side all worked up. They went into the comments gloating about how clear the relics would be. Since the new images have been released, I have been bombarded with emails from both sides of the fence wanting to know what I think of the new images. The supposed landing sites photographed were Apollos 12, 14 and 17, and their distances from the LRO turned out to be closer to 25 kilometers, rather than 20. Flipping back and forth between these 25km images and the earlier pictures from 90 kilometers and 50 kilometers, the landscape features on Apollos 12 and 17 are by all means an improvement. They appear a lot sharper, and there is no vertical stripe pattern running through them, as was evident in the 50km and the 100km images. You can distinctly make out the texture of the craters. These two sites are quite the improvement. Apollo 14 is a different story. Whilst browsing through the LRO website, I came across this image of the Apollo 14 site. When I first saw this, I thought it was the 20km image, but then I checked the date and saw that the so-called LEM looked quite different. This image was photographed on January 25, 2011, a good 7 months before the LRO dipped into its 20km orbit. In fact, the LRO principal investigator, Mark Robinson of Arizona State University, even blogged about this photo on February 4, 2011. In their press release of the 20km images, NASA featured the new images of the Apollo 12 and 17 sites alongside past LRO images of these locations for comparative purposes. Yet no past images of the Apollo 14 site were included in this article. In fact, the January 25th image is not even listed in NASA's online gallery for images of the Apollo sites. We wondered why. The January 25th image shows a much wider area than its 20km counterpart. We'll zoom in so that the two line up on top of each other. Now let's flip between the two. Flipping between the two, it is clear that the resolution in the two images is exactly the same. Both show the same level of detail, and both lack the vertical striping. What, did they forget to add them or something? If the resolution at 25 kilometers is supposed to be twice as clear as the 50km resolution, why does the clarity of the landscape look exactly the same in these two images? If it was exactly the same, what was the whole point of dipping into this lower orbit? Or did the LRO even dip into this lower orbit at all? Even if we ignore these obvious resolution similarities between the two and just accept the clarity of the images, the alleged man-made equipment, however, is a whole nother story, as it doesn't look much better than it did in the earlier 50km images. The Apollo 12 LEM looks little different than it did at 50 kilometers. Apollo 14 is so dark you can barely tell anything is there, and the Apollo 17 LEM is a slight improvement at best. And at 25 kilometers, the Apollo 17 LEM looks more like a pile of rocks than something man-made. There is another oddity between the two Apollo 14 images at 25 kilometers and 50 kilometers. In the 50km image, the LEM looks like a broken concrete cylinder casting an elongated shadow. In the 25km image, it's extremely darkened and shows no elongated shadow. The lack of an elongated shadow generally means the sun is shining directly overhead, but in all examples I've seen of such, the shadows within the craters are greatly, if not completely, diminished. Here, other than a few craters, it is clear that the shadows within the craters are the same length in both photos, particularly the big craters in the top right and lower bottom, and the smaller to medium-sized craters just north of the pixels that we're supposed to believe is the Alsep. This tends to suggest that the sun is coming in from the exact same, or at least a very similar angle, in which case the LEM should be casting an elongated shadow in both. And yet only the old image has this effect. As mentioned, this new orbit was temporary. NASA says the LRO only spent 1 month at 25 kilometers, photographing a small percentage of the moon at higher quality before returning to its earlier 50km altitude. The obvious question though is, why? Why not remain at 25 kilometers and photograph more of the moon at this obviously better quality? Or at least, what we're supposed to believe is obviously better quality. And if there is some valid reason for returning to the higher orbit, why not at least wait until all 6 Apollo sites have been photographed, rather than just 3 of them? Especially considering that these regions are obviously the high point of attraction for most people. Strangely, nowhere is any explanation given. Something else is odd here. In the earlier 50km and 100km orbits, we are always given access to large TIFF files labelled as raw images. Take for example this Apollo 17 image taken from 50 kilometers. This file spans an area 2,680 meters wide and 27,680 meters long. But for the 25km Apollo 17 image, we only have this region spanning 400 by 300 meters. To illustrate their comparative sizes, this red rectangle represents the area of the latest Apollo 17 image when overlaid on the previous full image taken at 50 kilometers. Small, isn't it? Are we to believe the LRO only photographed miniature portions of real estate this time round? Or are there much larger images that we're not being given access to? In early September, a teleconference was held to give out further information about the latest LRO acquisitions and invite interested members of the public to call in and ask questions. I booked a place to get in on the conference and had a short list of questions prepared in the off chance that I was able to get through, except they never sent me the phone-in number. Of the 6 people that did manage to call in, none questioned the low image quality of the Apollo relics or asked why this new orbit was only temporary. Funny about that. In an earlier LRO video, I also brought up the GeoEye-1, a privately owned Earth-orbiting satellite. GeoEye-1 orbits at 700 kilometers and by all accounts takes better quality images than LRO can do at 50 kilometers. Here's a photo of Rome, taken by GeoEye-1. If we zoom in, it becomes immediately obvious that GeoEye has perfectly resolved cars, buses, even individual people walking the streets. Here's another example, this time showing Quelimine Seaport. Again, we can resolve cars, and even shipping containers and tiny boats. I didn't look at all the images, but there are many of them that perfectly resolve puny objects like cars and trucks and buses. The LRO pictures look even more pixelated than before compared to these. I like this photo in particular because it really pones NASA's arse. Here, we see a GeoEye image of Cape Canaveral, showing one of NASA's shuttles on the pad. The image not only resolves the tiny cars, but also the shuttle stack. Oh sure, a space shuttle is much larger than a car, but we can clearly resolve the nose cone of the solid rocket booster. Each solid rocket booster has a diameter of 3.71 meters, and there is not a single doubt that that's a solid rocket booster. And how about the cars? Cars on average are about 4.6 meters long, and we can clearly make out the windscreens, windows, hoods, trunks, etc. The descent stage of the LEM is 4.27 meters wide, 9 meters wide if you count the landing gear span. But all we can see in these photos is white pixelated junk. By any definition, the lunar modules should be immensely clearer in these LRO images. LRO was 50 kilometers above the lunar surface when taking these pictures, and GeoEye 1 was over 600 kilometers above the Earth when it took its pictures, and yet its pictures are clearer than LRO's. Comparing the GeoEye 1 to the 25 kilometer LRO orbit images, it does appear the landscape may now be of better quality. But the artifacts are a different story, because by all accounts, GeoEye 1 still takes clearer images of the cars than the LRO can do of the rover. And that's despite being 28 times further away and looking through the atmosphere. It certainly leads one to wonder, what the hell is going on here? According to the teleconference, the reason LRO can't get good resolution is because it's moving too fast. It's orbiting at 1640 meters per second, and at its 338 microsecond shutter speed, this causes blurring in the order of half a meter.
In this lower orbit, our pixel scale is 25 centimeters because we're twice as close to the surface, but that's 25 centimeters in the cross-track direction. However, in the down-track direction, we're somewhat limited by the smear because the spacecraft is traveling so fast. It's 1,640 meters per second. And despite the fact that we can take an exposure as short as 338 microseconds, and that was microseconds, not milliseconds, in that short period of time, the spacecraft has moved 50 centimeters. So we get these rectangular pixels, which is a little odd if you viewed them that way. However, we just simply resample them into square pixels. And so the images you're looking at today have been the 25 by 50 centimeter pixels have been resampled into 25 centimeters square.
But GeoEye 1 moves at 7,500 meters per second. That's 4.6 times faster, and yet it takes better pictures. So again, what's going on? Thing is, this whole motion blur argument is a poor excuse. Any photographer knows it can easily be overcome by panning the camera to follow the target. For example, this car was captured while holding the camera still. The background is fine while the car is blurred. Whereas this was taken while panning the camera to follow the car. In this case the background is blurred, but the car is in focus. Presumably GeoEye 1 does something similar by rotating itself as it takes the picture. There's no reason why the LRO couldn't have had the same ability built in. In summary, despite all the hype, the LRO's so-called 25cm per pixel images show no better resolution than its earlier 50cm per pixel images. And the supposed artifacts therein are even less to be impressed about. In the next video, we'll show how these artifacts are by all means anomalous.